As we start to look at ionization energy and electron affinity, remember the two general trends that are used to explain changes in the properties. Horizontal trends are explained using nuclear charge or effective nuclear charge. Vertical trends are explained using the shell number or the value of the quantum number n. The ionization energy is the energy needed to remove an electron from a neutral gaseous atom. It is also called the first ionization energy. The energy needed to remove the second electron is called the second ionization energy, and so on. As one goes down a column, less energy is required to remove the first electron. The reason for this is that the energy level of the valence electrons gets higher as we go down the column, while the effective nuclear charge remains essentially the same. The trend going across a row is more difficult, but generally ionization energy increases as we go across a period. This is because the effective nuclear charge increases as we go from left to right across a row. There are two apparent exceptions to this general pattern, however. The first occurs with group 13. Group 13 begins the p block, so the last valence electron is in the p subshell rather than the s subshell. This means that the electron is in a higher energy orbital. The electron is also a little bit further away from the nucleus, and there is a bit of repulsion from the s electrons. All of these things reduce the energy needed to remove the electron. The second exception occurs with group 16. The electrons are in the p subshell, but group 16 has one orbital that contains two electrons. The repulsion from this electron helps in the removal of the other electron, so the ionization energy is lower. When we remove other electrons from the atom, it takes more and more energy to remove each successive electron. When we have removed all of the electrons from the valence shell, there is typically a big jump in energy needed to remove the next electron. So when we look at the first few ionization energies of an element, we can usually determine how many valence electrons an atom has. The electron affinity is the energy change associated with the addition of an electron to a neutral gaseous atom. Energy is usually released when the electron is added because the negatively charged electron is coming closer to the positively charged nucleus. The process is usually exothermic, so the energies are usually written with a negative sign to indicate this. The general pattern is much the same as the pattern for ionization energy, with the magnitude of the electron affinity increasing as we go from left to right across the table and as we go up a group. There are two exceptions to the pattern in addition to the noble gases, which are an exception because the electron needs to go into the next shell. The first is going from group 1 to group 2, where the electron affinity decreases. Group 2 has a filled s subshell, so the added electron must go into the p subshell, which has a higher energy. In addition, the electron is a bit further from the nucleus and feels some repulsion from the s electrons. All of these reduce the amount of energy released. The second exception is going from group 14 to group 15. Group 15 has one electron in each of the p orbitals, so the next electron must be paired with an electron in one of the orbitals. This creates repulsion that reduces the energy released. One other point to note is that as we go down the group, the orbitals get larger, which reduces the repulsions. This is why the difference between group 14 and group 15 decreases as we go down the column. There are two other properties that are worth mentioning. Both are related to the periodic properties we have looked at already. The first is the metallic character of elements. In any row, the elements on the left are metals. The elements on the right are nonmetals, and the elements in between are metalloids. Within a column, the nonmetals are at the top, and the metals are at the bottom, with metalloids in between. This leads to the observation that metallic character increases as we go to the left in a row and as we go down a column. Why would this be true? The single characteristic that most clearly identifies an element as a metal is the ability to conduct electricity. This is related to the ionization energy of the element. The easier it is to remove the electron from an atom, the easier it is for the substance to conduct electricity. Elements are more metallic the lower the ionization energy is, and the metallic character of the element follows this trend in ionization energies. The second property is reactivity. This property is split in the periodic table and has different patterns for metals than for nonmetals. For nonmetals, with the exception of the noble gases, the reactivity increases going up a group and going towards the right. How do we explain this trend? Typically, nonmetals react by adding electrons and releasing energy. This means that the more energy is released, the more reactive the element is. The trend follows the trend of electron affinity and explains why the noble gases are not part of this trend, since their electron affinities are positive. For metals, on the other hand, the reactivity increases to the left in a row and down a column. Why should this be true? Metals typically react by losing electrons and becoming positive ions. The lower the ionization energy, the easier it is to make the positive ion, so the trend follows the trend toward lower ionization energies, which is toward the left and down.